So I'm very honored by the invitation to speak in honor of Dale. Thank you very much. So this is the second part of a two-part talk. The first part was given by Sandrine Caruso last night, but don't worry, I mean, I will try to summarize everything from her talk, which you will need to know for this talk. Okay. The main result is the following. Roughly speaking, generic braids have Pseudo-Anosov. More precisely, if you look at the Cayley graph of the braid group, Bn, of radius L centered in the trivial element, and you take as the generating set the set of simple braids, also known as positive permutation braids. I will explain them in more detail later. That's also known as Garside's classical generators. That's a generating set which contains in particular all of Artian's well-known generator sigma I, single crossings. Then the proportion of Pseudo-Anosov elements in this ball tends to 1 exponentially fast as the radius of the ball tends to infinity. It should be pointed out that the slogan generic braids are Pseudo-Anosov can be interpreted in various ways. The most well-known of these are you take as a generic braid the result of a long random walk in the braid group with your favorite generating set. In that case, the analog result was already proven, and actually a lot more was proven by independent work of Ma and Sisto. Let me say immediately that the result is kind of unsatisfying. For one thing, it is totally dependent on that particular choice of generating set, which it shouldn't be. We can't even prove that generic braids in the pure braid group are Pseudo-Anosov. They clearly are. We can't prove anything about general mapping class groups. Or what you would actually like to do is to generalize the result of, say, of Sisto. If you have a group acting on a delta hyperbolic space, then under some very weak hypotheses, a generic element should act loxodromically. Don't know how to prove this. So I think we're both very open to suggestions for collaborations. Now, the positive results. The first corollary, which is amusing, is there are arbitrarily large balls in the Cayley graph which contain only Pseudo-Anosov elements. That's actually a fairly easy exercise to deduce that from the main theorem. What you need is essentially that the braid group has exponential growth. I'm sorry? Oh, of course, yeah. These balls are not centered on the origin. Definitely not. Thank you. Does that also just follow from general Nielsen-Thurston theory? You're saying in a large neighborhood of a massive power of a Pseudo-Anosov, you only get Let's talk about that. I didn't know that argument, but very good. Another corollary is that the closure of a generic braid, generic always in the same sense. Take a random element with uniform probability in a large ball. Of a generic braid is a hyperbolic link in the sense of, Thurston. So let me remind you, the closure of a braid is simply you take your braid and you close up the strands in the obvious way to obtain a link. The proof of the corollary, it uses a result of Tetsuya Ito, which says that if you take a Pseudo-Anosov braid, then its closure is automatically hyperbolic, provided the Dionwa floor of the braid is not in the interval -2, 2. What that means is in the Dionwa braid ordering, the braid does not lie between delta to the -4 and delta to the 4. So in order to prove the corollary, you have to prove that a generic braid does not lie between delta to the -4 and delta to the 4 in the Dionwa braid ordering, which is not terribly difficult. There's another theorem which I will probably not have time to talk about. Generically, the conjugacy search problem in the braid group Bn can be solved in quadratic time. What do I mean by that? Okay. There exists, okay, you give me 2 braids. I have an algorithm. Okay, 2 braids of length L, or the longer one is of length L. There's an algorithm which computes time proportional to L squared and which can give me 3 possible outputs. Either it says the 2 braids are conjugate and here is a conjugating braid. Or it responds the 2 braids are not conjugate and here is a proof that they are not conjugate. Or it replies, I don't know. Which does not sound like a great theorem, but the point is that, that the answer, I don't know, occurs exponentially rarely. So among the set of pairs of braids of length L, the proportion of pairs where the answer I don't know occurs decreases towards 0 exponentially quickly as L goes to infinity. Okay, the proof is all Garside theory, so I have to tell you something about Garside theory. So our preferred generators of the braid group are those simple braids, which I already mentioned, positive permutation braids. By definition, these are braids with only positive crossings where any 2 strands cross at most once. The set of braids is in bijection with the set of permutations of the numbers 1 to n, hence the name. Let me give you a typical example to see how that works. So I take no, let's go to that side. Four, 2, 4, 1, 3. 2, 4, 1, 3. Okay, 4th strand goes to 2nd position, 3rd strand goes to 4th position, and so on. And if you start drawing them from the right, you get automatically only positive crossings. There's a very particular example, very important in the whole theory, which is the half-twist braid delta. Which corresponds to the permutation which just reverses the numbers 1 to n. This braid has an important property. It like almost commutes with braids. So delta squared actually generates the center. And that braid has the property, let me draw a picture. A delta B C equals, you can push the delta around the only thing that goes kind of wrong is that your letter B is flipped like that. And it's conjugated by delta, and that is, we didn't call that automorphism of the braid group tau, conjugation by delta. Okay. Definition. We say that the sequence of two simple braids is left-weighted if you cannot pull any crossing from a later factor into an earlier factor. At least not without destroying the property that the earlier factor is simple, that any two strands cross at most once. So in this example here, the first example, this is not left-weighted because this crossing here can be pulled up into the first factor x1, and you see that if after you pull it up, the first factor remains a simple braid. Any two strands cross at most once. The second factor is, of course, still a simple braid. And now it is left-weighted. You cannot pull any more crossings up into an earlier factor. And now if you start with any long braid written as a product of simple braids, so a positive braid written as a product of simple braids, and you apply this procedure, so you just keep pushing crossings into earlier factors as much as possible. Well, you keep going, and at some point you get stuck. That is, at some point you arrive at a left-weighted braid. Any two subsequent factors are left-weighted. And the wonderful theorem is that this procedure is confluent. If you start with any, well, given an element of the braid group, positive element, you start with any representative of it, you pull crossings back into earlier factors, in any order you like, you always end up with the exact same writing of the braid. Same sequence of, same product of simple braids. So that's the main point of this theorem. Every element in the braid group, now no longer necessarily positive, has a unique representative of the form some power of delta, which may be negative, followed by a left-weighted positive braid. That number k is called the infimum of x, the number of non-trivial or non-delta factors is called the canonical length of X. Another way to see this is that normal forms are described by a finite state automaton. Let me give you the automaton in the case n equals 3. So an arrow indicates that, well, this factor can be followed by this factor and it will be left weighted. That's the finite state automaton. Thank you. That's the finite state automaton for n equals 3. And already for n equals 4. The picture gets extremely complicated. Sandrine showed it last night. Don't hesitate to ask questions. Quadratic time. It takes quadratic time to find the unique representative. You just pull crossings, pull. The right way to do it is you have a braid which is already in normal form. You add a new factor to the end and you just push crossings back as far as possible. And yeah. Yes? Okay, that was the finite state automaton for just the positive part. Indeed, it can be, then any braid can be written by any positive or negative power of delta followed by that. And I should say that that point of view allows you then to have good counting arguments for braids. If you want to count the number of positive braids, to count the number of braids which avoid certain sub-patterns and so on. Well, the thing to do is you write down the adjacency matrix of that graph, and then you use Perron-Frobenius theory. And Sandrine talked about that in some detail last night. Okay, a rigid braid. Well, let's first define it just for a braid which does not have any factors delta in the beginning. It is rigid if the last factor followed by the first factor is left weighted. That is, if you close up the braid, you get a braid which is in normal form everywhere. Which is left weighted everywhere. If you have a factor delta to the k in the beginning, well, the idea is you have to first push the delta to the k out of the way so that it no longer sits between the last factor and the first factor. And then it's the same criterion, then it's the same definition. Okay. So a quick reminder of Nielsen-Thurston classification. Every braid is exactly one of the following. It can be periodic, which in our context you have to adapt the obvious definition of periodic a little bit. There exists some power of the braid which is equal to some power of, I should have better said delta squared. Yeah. Okay, some power of the braid is equal to power of delta squared. Second possibility, it is reducible, that is, there's some curve system which is preserved. Since braids can be both periodic and reducible, let me just exclude reducible periodic ones from the second case. And the third possibility is Pseudo-Anosov. And for the purposes of this talk, a Pseudo-Anosov braid is by definition a braid which is neither periodic nor reducible. Of course, it has a much more interesting definition. Let me give you some examples of reducible braids. So this first kind of example is really the kind of thing that annoys us. A braid can be reducible. Well, if you want to recognize a reducible braid, this is really difficult. If you give me if you give me a braid, if I want to decide whether it is reducible or not, this is very much a non-trivial task. Because reducing curves may exist, but they look messy. And I have no easy a priori bound on how messy the curves can get in terms of the length of the braid or so. It does actually exist, but nothing obvious at all. So here you see an example of a curve which gets, as you push it down the braid, it gets deformed, 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 and ends up with exactly the same curve you started with. But you wouldn't have easily guessed that curve. And that braid is actually in its own supersummit set, which means it is as short as possible, as short as it can get within its conjugacy class. So even if you choose a reasonable representative within the conjugacy class of the braids, still reducing curves can look ugly. The second one, so that one is from a paper of Sang-Jin Lee and Yeon-Kyung Lee. I'm not saying that every shortest representative, wait, I'm saying, wait, if a braid is reducible, then any conjugate is also reducible, obviously. This braid is actually, if you look at the whole conjugacy class of the braid, well, every other element of the conjugacy class has at least as many factors. So it is as short as possible in its conjugacy class. Now it is true that there is some other braid which is as short as possible in its conjugacy class, which has nice round reducing curves. But how do you find that? Yeah. The second braid, so that example is from Sang-Jin Lee and Yeon-Kyung Lee, a husband and wife team in Korea who do some of the really important work in this area, and which we use for our work as well. So in this example, this braid is actually rigid, still, which is stronger than being as short as possible in its conjugacy class. So it's a really nice representative of the braid within its conjugacy class. And still, the reducing curves are not round. So this is bad. This is depressing news. This is the kind of thing we like. Okay, the third one is we have a nice round reducing curve, and it can actually be proven that if you have if there's some round curve which is preserved, then as you push the round curve down the braid, it will be round at every single step. That's an easily recognized reducible braid. Okay, our criterion, which we use for being Pseudo-Anosov. Well, let me first say the kind of vague. Hope is if you choose an element, well, given a braid, choose some conjugate braid which is as short and straight and nice and tight as possible as it can get within its conjugacy class. Then the only reducing curves, there should be nice, obvious reducing curves, not messy ones. And here is the theorem which makes this kind of makes the whole thing tick. That's a theorem of Juan and myself. A rigid reducible braid has either nice round reduction curves or, well, I'm slightly lying here, but essentially it's this. There's a reducing curve which is what we call almost round. And in this case, the interior strands of this within the curve do not cross at all. Or they could form a delta within each factor. They could cross as much as possible in each factor. Let's ignore that case. And that second case actually occurs. That's was exactly what was happening here. You had a rigid braid. You had a curve here, which was not quite round, but almost round. And the two interior strands, so these two, if you look at them, they don't cross. So when Juan and I first saw this example, we were really depressed, and then we realized that's actually the worst thing that can happen. You were not, I was. Okay. And my feeling is that if we can't say anything about general mapping class groups, it's because we don't have any analog of that result. I don't even know what we should mean by rigid. So, if a rigid braid wants to be reducible, it must not contain both of these braids. So we have two braids here. Either, well, I have to distinguish the case n, odd, or even, but that is one braid, right? And the second braid is this one. Why must it not contain both of these braids? Because this first braid here, if you can just check quite easily by hand, it does not send any round curve to any round curve to a round curve. If you choose any round curve, like the one, I don't know, that surrounds these two punctures here, and you push it down the braid, well, you do not get a round curve. And this braid, the second braid, well, every pair of strands crosses. So that cannot be part of a braid which preserves an almost round curve with all interior strands not crossing, because in this braid any two strands cross. Okay, so these two braids exclude exactly the two possibilities here. Just for rigid braids. Yes, it could contain one of them because, well, it could be that, for instance, it could contain the first one. That would mean that no round curve can be preserved, but that doesn't matter because an almost round curve could be preserved with all interior strands trivial. Yeah. Now, however, if you look at a generic braid, well, if you look at a long, long braid, well, you can be very sure that somewhere in that long braid, these two sub-braids will appear just by chance. So what Sandrine talked about in some detail last night was the justification of that, the proportion of braids which avoid these two sub-braids tends to 0 as the length tends to infinity. Does that make sense? It tends to 0 exponentially quickly. So the theorem which we heard last night was among the braids in the L ball, in the ball of radius L centered on 1 in the Cayley graph, the proportion of rigid Pseudo-Anosov braids is bounded below by some strictly positive constant. Why is that? Well, as the length to infinity, as the length tends to infinity, the proportion of rigid braids tends to some strictly positive number. Definitely not to 1, but to some strictly positive number. Why is that? Well, if you fix the first factor and you look among all braids of length L, which simple braids occur with which frequency as the last factor of that braid, you get some distribution, some probability distribution on the set of simple braids, and as the length tends to infinity, that tends to some stable probability distribution on the set of simple braids. It's just Perron-Frobenius theory. And actually, that probability distribution is even invariant. It doesn't even depend on the first factor we chose, but I won't use that. Now, the question whether or not a braid is rigid depends only, a braid's written in normal form. The question on whether or not it is rigid depends only on the first and last factor. So, for any given first factor, there is some definite positive probability that the last factor will be one of the factors that makes the whole thing rigid. There's a positive probability that the last factor will be a simple braid with a property that last factor followed by first factor is left-weighted. So, the probability that a long braid is rigid is some strictly positive number, and among the rigid braids, the probability that it will not be reducible tends to 1. That's what we just saw in the whole previous argument, because it will probably contain one of those two reducibility destroying sub-braids, or because it will contain both of these reducibility destroying sub-braids. In total, the proportion of rigid Pseudo-Anosov braids tends to some positive number. Questions? If it contains both of these, then it is exactly irreducible. Oh, and I should have mentioned the periodic case, but that's not a problem at all, because the only rigid periodic braids are actually powers of delta. So forget it. Okay. Let's look at the idea of the proof of the main theorem. So we want to prove that that generic braids are Pseudo-Anosov. So, definition. If I have a conjugation of some braid x, written in normal form x1, x2 up to xl, and I conjugate it to some other braid x tilde, which in normal form is written x1 tilde up to xl tilde. Oh, I'm sorry, I shouldn't have made that the same L. That's not necessarily the same length. I say this conjugation is non-intrusive if, well, the middle third of that word here appears literally in pristine form, again, somewhere in the conjugated word. I'm not saying that it must appear right in the middle, because there could be some cyclic conjugation going on as well. But it must appear that middle, there must be some part of the center of that original word must survive, literally. So the idea is that what's a conjugation? Well, you take your braid x, you multiply it on the left by y inverse, on the right by y. And we say it is non-intrusive if these, well, if that only changes the conjugated braid near the two ends and doesn't really touch the middle. Now the claim is that generic braids are non-intrusively conjugate to rigid braids. That is, if I take some random element from the ball of radius L in the Cayley graph, then the proportion of braids that have some non-intrusive conjugation to some rigid braid tends to 1 exponentially quickly, actually. Let's first see why that claim implies the main theorem. Well, a generic braid can be conjugated to a rigid braid, and the middle third of the original word has survived in the conjugated braid. But that middle third, we can be pretty sure that that middle third still contains these two reducibility destroying subbraids. And that's the proof. That's all there is to it. Yeah. So, let's prove the claim. I'd like a really big picture. So let me draw a picture in the Cayley graph of Bn. Now x, our braid x, lifts to a bi-infinite path. So, whoop. I need to write explanations there. So. P1, P2, P3. P1, P2, P3, and so on. So each of them has lots of factors. Now, let us draw let us look at the normal form of the braid from here to here. So that is, can you see that? That's the normal form of P3, P1. Now I claim that generically its last factor equals the last factor of P1 and its first factor equals the first factor of P3. If that is true, then the claim is proven, because then, well, the braid that does, then the braid P2, P1, P3 is rigid. Oh, I'm sorry. Let me back up. That wasn't clear at all. What do I mean by that kink? I mean, by that picture, I mean every sequence of subsequent factors is left-weighted everywhere. The only place where where two factors can occur one after the other and not being left-weighted is at this transition from P3 to P1. That's what I mean by this kink. It does not mean that the braid is making some detour or so. It could very well be a geodesic. So by that kink, I mean not left-weighted. Yes? In the Cayley graph of Pn. And that is the lift of my word x. So I just write x, 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 x in the Cayley graph. Now, if the last factor of this blue braid is equal to the last factor of P1, and the first factor here is equal to the first factor of P3, well, then P2, the normal form of P2, followed by the normal form of P1, is a braid which is conjugate to the original braid X and which is now rigid. Because just if I go along P2 followed by the blue line, followed by P2, followed by the blue line and so on, it's just left-weighted everywhere. Now, why is that true, that generically its last factor is equal to the last factor of P1 and the first factor is equal to the first factor of P1? Well, I claim that somewhere in the second half of P1, I mean not right at the start, but somewhere rather near the end, say in the second half of P1, there is something which we call a blocking braid. Alpha. Blocking braid and something analog over here. Let me not discuss that in detail. So the way I think of this is you have this braid here, and somewhere in the middle of it, there's a point where it is not left weighted. So you start applying your algorithm of just pushing crossings back along the braid. So now some crossings of P1 will be eaten up by P3. But I claim that very probably there's something here along the way which stops this the pushing of braids. Okay, P3 cannot eat arbitrarily far into P1 because there's a blocking braid. So here's an example of a blocking braid. So the defining fact is, well, there's a sigma 2 occurring. You could have replaced that with anything else. But if you take any braid x such that x times alpha is a normal form, as written, then the only simple suffix of x times alpha is the thing that was already the last factor of the blocking braid. In other words, if you take the right normal form, if you push all crossings as far to the right as possible, instead of as far to the left as possible, as is more usual, then still the last factor will contain only the sigma 2 and nothing else. You can't push it. Somehow the alpha blocks crossings from being pushed further to the left. Yes. Yes. I need blockings on both sides, and I wasn't planning on telling you exactly what that means on the left side, because crossings are being pushed to the left side. So the blocking property I need is a slightly different one, but actually there's a perfect duality between the 2 points of view. P1 and P3 actually deep down play completely symmetric roles. Okay, so if we call in that picture everything that I don't know if you can see that. That part is X, everything that comes before the blocking braid. So, P3 will eat part of X alpha. But what remains is still a suffix of X alpha. So, any suffix of what remains after the eating is still a suffix of X alpha. So it's sigma 2. So, let me try to summarize this. There are two things that can happen. It could, of course, happen by accident that P3 eats all of this braid, up to and including alpha. By some terrible coincidence, that could happen. But as alpha, I said, occurs in the second half of P1, we can prove that this is actually extremely unlikely. The other possibility is that P3 does not eat all of that braid, in which case, starting from that point here, the simplification will leave all that remainder here intact. I hope I kind of got the idea across. Oh, I actually have 5 minutes left. Questions? Okay, so I hope I tried. It all kind of falls together. That was supposed to be the end of the proof of the main theorem. If I have time left, I can say a few words about the proof of theorem too. But you had a question? No? Sorry. Let me remind you then of theorem 2. Generically, the conjugacy search problem can be done in quadratic time. Okay, here's what we actually prove. Generically, now this is probably more for the specialists. Generically, if you take any one braid from the from a large ball of the Cayley graph, in the Cayley graph, very probably its sliding circuit set is as small as it can possibly be. So we have all these these characteristic subsets of the conjugacy classes of braid groups, and the most famous one is the supersummit set, and there's another one called the sliding circuit set. What you should know about this is that if a braid is rigid, if a braid has a rigid conjugate, then the sliding circuit set, whatever it is in general, is exactly the set of rigid conjugates. Okay? So if a braid has some rigid conjugate, then there's a look at the set of all rigid conjugates. I claim that if you take a generic braid, well, I already convinced you, I hope, that the generic braid is conjugate to a rigid braid, actually by a non-intrusive conjugation. And moreover, what we prove is that generically, this rigid conjugate contains some other subbraid which prevents the set of rigid conjugates from being large. It forces the set of rigid conjugates to be very small. It contains only the set of, well, this braid we just found, plus the obvious other elements, which is the cyclic conjugates and the conjugates by delta. So that forces this characteristic subset to be small, and that makes the conjugacy search problem easily solvable. That's the rough idea of that result. Okay, thank you very much for your attention.
Are there questions?
Thank you. Bert, if you take the line at the top of a braid containing all the initial points of the strings, push this line down the braid so that it comes to the bottom, and it's now a wiggly line, and it passes through all the bottoms of the strings, okay, but in some distinct order.
Yeah.
I was thinking about the problem of trying to spot a round circle which is preserved. Would that be an easier task? Because you'd have the round circle would be again at the bottom, and everything maybe the line will wiggle round inside the disc. Have you thought about that as a method of looking for?
You mean rather you want to use that rather than putting the braid into Garside normal form?
Well, no, I'm just trying to think of how to spot for reducible circles.
I mean, if you want to spot reducible circles, I mean, once you've put the braid into Garside normal form, it's very easy. You simply try out all the round curves. They're only quadratically n squared of the order of n squared, if n is the number of strands. And you push it down the braid, and it must be round after each factor and must arrive round. I think if you try to do it directly from the curve diagram, I haven't really thought about this, but that sounds unnecessarily hard to me. But any ideas, my co-authors?
Your point there that you're going to be handling braids that have massive numbers of crossings and things. When you
Well,
down a line of that sort.
Okay.
Are you doing it by hand or are you doing it by machine?
Oh, so Hugh's question was, he didn't have the microphone, you have some massive number of crossings, you push your line down, do you do it by hand or by machine? Well, I mean, if you actually try to, okay, I think here's a negative answer to Roger's question. If you actually want to calculate the image of the line, I wanted to say that takes exponential time. That's not true. That takes, you can do that in quadratic time. That's what Ivan told us. But you will get the image of the line in some funny code where it is really not obvious to. I don't see how to read off from the complicated line at the bottom whether a circle was preserved. I haven't thought about it. Maybe you can read. So Juan, you think it can maybe be read directly from Dinikov's coordinates? If it's a round curve, I'd have to think about it. Yeah.
Other questions? Okay, let's thank the speaker again.